Hi everyone, welcome to the 2.4 lecture on Venn diagrams with three sets and verification of equality of sets. In the past lectures, we looked at Venn diagrams with at most two sets, so now we're going to extend our knowledge and look at three sets and creating a Venn diagram, which can be a little bit more challenging. There's really no set way to fill in the Venn diagram when you have three sets, but your book does give a recommendation, which you're free to look at on page 68. We're going to follow some of the steps from the book's recommendation, but not exactly. So we're going to start out by looking at a problem. And if you need to read the problem on your own, please feel free to pause the video and then unpause it when you're ready to go over the problem. Human blood is classified or typed according to the presence or absence of the specific antigens A, B, and Rh in the red blood cells. Antigens are highly specified proteins and carbohydrates that will trigger the production of antibodies in the blood to fight infection. Blood containing the Rh antigen is labeled positive, while blood lacking the Rh antigen is labeled negative. Blood lacking both A and B antigens is called type O. Sketch a Venn diagram with three sets, A, B, and Rh, and place each type of blood listed in the proper region. A person has only one type of blood. So, in order to create my Venn diagram, I'm going to first draw a rectangle with three circles. Now I already have one created in one of my other notes. So I am going to copy and paste that and put it in our notes to make it easier and more clean. Okay, so here's my Venn diagram. And I'm going to label each of these circles. So I have my A, my B, and my RH. And then of course we have our universal set. Now I need to figure out where everything is placed. So in the problem, they talk about type O blood, which is lacking both A and B antigens. So I know that O is going to go on the outside of the A and B circles. So that means that my O blood is going to go either in this region here, or it's going to go in the part of the universal set that doesn't contain the circles. So because it's on the inside, we know that it's going to be O positive blood. And on the outside is going to be my O negative. Now, if you look at just circle A, circle A is going to contain the A type blood. So that's going to be either A positive or A negative. If you look at this region here, this is where all three circles come together. So what's going to go in there is my A, B positive. In the region right above it, it's going to be my A, B negative. And remember, it's negative because it's lacking the RH. So it's not intersecting the RH circle. Next door to it on the left is going to be my A negative because, again, it's lacking the RH. It's not that part of the A, this part here, is not intersecting the circle with the RH. The same thing with the AB negative. So that's why it's negative. And then all that's left to go here would be my A positive. And then the same thing's going to be true with the B. except this is going to be B negative because that circle, that part of the circle, is not intersecting the RH. So if you look at this part of the circle here, it's not intersecting with the RH circle. So that means it's negative. This part, however, is intersecting with the B and the RH, so it's positive. And that completes the circle for the Venn diagram of the 3 different blood types. Now we're going to look at how to verify the equality of sets. So your text sometimes refers to the operations on the sets as statements involving sets, or they'll simply refer to them as statements. So when you hear statements involving sets or statements, they're really referring to operations on sets. So if you'll recall, this operation right here is saying A or B complement. And if we're talking about B complement, remember that means anything that's not in B. And then if we're looking at this statement, that is just saying the intersection of A and B and C. And if you look at this diagram here, the intersection of all 3 of those sets would be where it's A, B positive. So we're talking about in this region right here, region 5 is where all 3 sets would come together. How do we determine if two statements involving sets are equal? So we're going to look at this question. Is A complement or B equal to A complement and B? So is the union of A complement and B the same as the intersection of A complement and B? So here we're talking about the union, and here we're talking about the intersection for all sets A and B. So that means for any set A and B, no matter what numbers are in those sets. So we're going to look at that right now. So for example, if we have specific sets, our universal set is 1, 2, 3, 4, 5, and set A is 1 and 3, and set B is 2, 4, and 5. So now we're going to answer that question. So if I look at A complement, if A is 1 and 3, that means that A complement has to be anything but that. So it would be 2, 4, and 5. And we already know that B is 2, 4, and 5. So now to answer this question, is A complement or B the same as A complement and B? So or means you need a union. You need one of everything. So if I was to look at A complement and B, they both have a 2, they both have a 4, and they both have a 5. So if I put those together, the 2 sets would be 2, 4, and 5. For A complement and B, we're looking at the intersection. Well, they both have a 2, they both have a 4, and they both have a 5. So the intersection is also 2, 4, and 5. So this would lead you to believe that A complement or B is the same as A complement and B. However, if we change our sets, this might not be true anymore. So for this particular set, the answer is yes. They are the same. But we want to make it general for any set. So I'm going to prove that this is not always true. Let's say I change my set A to be 1, 3, and 5 instead of 1 and 3. So I'm going to add an extra element. And let's change B to 2 and 3. Let's see if it works now. So if I find A complement, we know that that means it can't be 1, it can't be 3, and it can't be 5. So all that's left from the universal set would be 2 and 4. And for B, it's 2 and 3. So now, if I want to find A complement or B, I need one of everything. So I need a 2, I need a 3, and I need a 4 if I look at both of those sets. And A complement and B is the intersection. The only place they intersect is 2. As you can see, both of these sets are not equal. So therefore, that is a counterexample. You just disproved that A complement or B is not the same as A complement and B. When we prove things like this, we're using what's called deductive reasoning, which begins with a general statement. So our general statement here is A complement or B equal to A complement and B? And we work to a specific conclusion. So we found a counterexample. We found a time when that is not necessarily the case. So we can use deductive reasoning and also Venn diagrams to determine whether set statements are equal for any two sets selected. And we're going to use the regions and the Venn diagram to help us. So let's take a look at this statement now, and let's actually use a Venn diagram to prove it. So we're going to determine whether A and B complement is equal to A complement or B complement for all sets A and B. So I've got two sets, A and B. So we're going to draw two circles inside the universal set. So here's set A, here's set B, and of course here's my universal set. And we've got our regions 1, 2, 3, and then we have region 4. So I'm going to make a little table. I've got set A, and I want to know what region set A is. So set A takes up this entire region of 1 and 2. Set B is regions 2 and 3. And I want to know is the complement of A and B equal to A complement or B complement. So first let's find A and B, and then we'll take their complement. So if you'll recall, A and B is an intersection. Where's the intersection at? The intersection is right here in the middle. So the region that A and B take up is 2. That's where they intersect. So then what would the complement of A and B be? It's anything but region 2. So it's region 1, 3, and 4. Now we're going to do the same thing, except we're going to prove the other side of the equation, A complement or B complement. So I'm going to have A complement now. And what region would A complement be? Well, that's anything but A. So remember, A is made up of 1 and 2. So A complement would be region 3 and 4. B complement is made up of, well, B is made up of 2 and 3. So B complement would be made up of 1 and 4. And now I want to find A complement or B complement. So or means put them together. We need one of everything. So if I look at my A complement, I've got a 3 and 4, and B complement's a 1 and 4. So when I use an or, I need to combine them and have one of everything. So I would have 1, 3, and 4. Now if I compare this to this, they're the same. So here we just proved that the complement of A and B is actually the same thing as A complement or B complement. And this is actually from what's called De Morgan's laws, which we're going to talk about here in a second. So De Morgan was a mathematician, and he found that if you take the complement of an intersection, it's equal to the union of the complement of each set. And here are De Morgan's laws. So De Morgan's laws make it possible to transform statements and formulas into more convenient forms. We use this in set theory. You'll see it again in logic when we get to chapter 3, and other branches of mathematics like probability and statistical theory. So his laws are the complement of A and B equals A complement or B complement. And this is the one that we just proved. What we're going to prove now is the second law, which says A or B complement, so the complement of A or B is equal to A complement and B complement. So that's his De Morgan's second law, and we're going to prove that now. We're going to use the same way that we proved De Morgan's first law. So I'm going to draw my rectangle and my two circles. And I've got my regions, I'll keep the same. 1, 2, and 3, and then 4. And this is the universal set. Okay, I'm going to break this down just like I did in the last example. We've got our set and our region. So the first thing we want to show is A. Set A is made up of regions 1 and 2. Set B is made up of regions 2 and 3. And now I'm looking for A or B. So or means to combine them. So it would be set 1, 2, and 3. And we talked about that in one of our previous lectures, that if you want to take A or B, it's just the 3 circles added together. So region 1 plus 2 plus 3 always gives you A or B. And now, according to De Morgan's law, we are going to prove the complement of A or B. So the complement of A or B would just be anything that's not region 1, 2, and 3. So the only region that's not 1, 2, and 3 would be region 4. And now we're going to prove the other side of the equation, which says A complement and B complement. So we're going to look at A complement, which would be anything that's not A. So A is 1 and 2, so anything that's not A would be 3 and 4. And not B would be anything that's not 2 and 3, so that would leave us with 1 and 4. And then not A and not B would be the intersection of both of those. So they intersect at 4. So therefore, and by the way, the symbol for therefore looks like this, if you ever see that. It's like a triangle of circles. Therefore, A or B complement is equal to A complement and B complement. Okay, everybody, that concludes the lecture for 2.4. I hope you all learned something from it. And again, if you need any extra help, please feel free to contact me. You can sign up for my office hours through the homepage on Canvas. You may also send me an email if you have a question that could be answered that way. Hope you all have a great rest of your day.